So we're given a plate with a constant density of 2 grams per centimeter squared, and it's in a shape bounded by the curves y equals x squared and y equals square root of x, where x and y is in centimeters. We're going to find the total mass, and then x bar and y bar the center of mass. And just to get an idea of what we're looking at, we have x squared here, and square root of x here. So there's our y equals x squared, or y equals square root of x. So we're going to have a lot of symmetry on this. So x bar and y bar are going to end up being the same in this case, but we'll talk about how you could do it if you weren't sure or they weren't going to be the same. But let's start with the total mass. The total mass is going to be the integral of the density times the area in terms of x of our plate. Well, we're going to need where these intersect, and they intersect at 0, 0, and they happen to intersect up here at 1, 1. And we're going to do the area in terms of x, although we could do it in terms of y, because the density doesn't depend on either x or y. It's a nice constant density. So we'll put our density in there. And then the area, is we can treat it as area between two curves, square root of x minus x squared dx. This is going to go from 0 to 1. So we actually don't get too bad of an integral. 2 times 0 to 1, x to the 1/2 minus x squared dx. We'll do this one piece by piece. X to the 1/2, the antiderivative of that is 2/3 x to the 3/2 minus 1/3 x cubed from 0 to 1. We don't have to worry about the 0 is going to zero everything out. So if you see what's going to happen when we put the 1 in, we're going to have 2 times 2/3 minus 1/3, or 2 times 1/3, which is 2/3. And so the mass is going to be 2/3 grams. Now to get x bar or y bar, you need the moment divided by the density. Now because we've already set up the area in terms of x, it's going to be very easy for us to get x bar. It's going to be the integral of basically this integral here, but multiplied by another x. So 2 times x times square root of x minus x squared dx. That'll calculate the moment. And the mass we already calculated at 2/3. So I'm going to collect my constants here. Dividing by 2/3, same thing as multiplying by 3/2. So 3/2 times 2 times the integral from 0 to 1. If I distribute this through, it's going to give me x to the 3/2, because x to the 1/2 times x to the first is x to the 3/2, minus x cubed dx. We can simplify this a little bit. Let's go ahead and take our antiderivatives. So we'll have 2/5 x to the 5/2 minus 1/4 x to the 4th. We're going to have a similar situation to before, in that we only really need to plug in 1 because our lower limit 0 zeroes the whole thing out. So we're going to have 3 times 2/5 minus 1/4. So 3 times, let's go put these into 20ths to get a common denominator. 8/20 minus 5/20 gives us 3 times 3/20, or 9/20, and our units on this will be centimeters. Now, it is going to end up being the same as y bar because of symmetry, but let's just say we didn't know that for sure. The way we would set up y bar is we'd need to do the moment for y. Let's just do it in general here. It would be delta times y times the area in terms of y, dy, over the total mass, which again we've already calculated. Now what you'll see is to do the area in terms of y, you need to solve your two equations for y. Well, if we do that, this one is going to give us x equals square root of y. X equals y squared. X equals y squared. This one will give us x equals square root of y. So when we go to do the area, we're going to end up with the exact same integral just in terms of y. which is why we're going to get the exact same answer. But this is how you would set it up if you didn't have this symmetry between x bar and y bar.